In 2019, a structural engineer in Boston was digitizing old photographs for the city's historical archive. Standard preservation work, scanning 19th century images of buildings, bridges, and construction sites. Then he saw something that made him stop. The photograph was from 1893. It showed the construction of a railway bridge outside Boston. Workers, scaffolding, partially completed stonework, nothing unusual, except for one detail. In the background, barely visible, was a crane. Not a modern crane, a 19th century lifting device. But it was positioned at an angle that shouldn't work. The load it was lifting, a multi-ton stone block, was at an extension that would require counterweight calculations that didn't exist in 1893. The engineer ran the numbers. The crane, as positioned in the photograph, should have toppled. The physics didn't work. Not with 19th century materials, not with the techniques documented in engineering manuals of that era. But there it was, in a photograph, lifting a block, functioning. He showed it to colleagues, civil engineers, mechanical engineers, historians of technology. Everyone agreed. According to modern structural analysis, that crane shouldn't work. And yet it did. That discovery led to a project, a systematic review of thousands of old construction photographs, images from the 1800s and early 1900s, from across Europe and North America. And what they found shocked them. Dozens of photographs showing construction techniques, machines, and structural methods that modern engineers can't explain. Not because the technology is too advanced, but because the techniques violate modern engineering assumptions. Buildings that shouldn't stand, but did. Bridges built using methods that seem impossible, but they're still standing today. Tools and machines that operate on principles we've forgotten or never learned. Welcome to The Financial Historian, where we follow the evidence because the past isn't as simple as textbooks claim. Today, we're diving into one of the strangest discoveries in modern engineering, old photographs that reveal techniques we can't replicate, methods we've lost, knowledge that disappeared when we transitioned from craft to industry. Because the photographs don't lie. They're physical evidence, proof that engineers of the 1800s were doing things we think are impossible. And the question isn't, how did they do it? The question is, what else did we forget? Let's start with something famous, the Brooklyn Bridge. Opened in 1883, one of the most photographed construction projects in history. Thousands of images document its construction from 1869 to 1883. The caissons, the cables, the towers, the workers, everything. And buried in those photographs is something engineers noticed in 2007 when the bridge underwent a major structural survey. The original construction photographs show workers installing the main cables. These cables are massive. Each cable is 15.75 inches in diameter, made of 5,434 individual steel wires bundled together. The 4 main cables support the entire bridge. Standard engineering practice today requires precise calculations for cable tension, load distribution, and thermal expansion, computer models, finite element analysis, stress testing. But in 1883, none of that existed. The chief engineer, Washington Roebling, calculated cable tension by hand using 19th century mathematics, pen and paper, and he got it right. The cables, as installed in 1883, still function perfectly today, 141 years later. But here's where it gets strange. Modern engineers, using computer analysis, tried to reverse engineer Roebling's calculations. They used the original construction photographs to determine cable placement, angle, and tension. The results were inconsistent. According to modern load analysis, some of the cable angles in the photographs shouldn't work. The tension would be uneven.
The load distribution would create stress points that should have caused failure within decades. And yet, the bridge stands. No major structural failures, no cable replacements. The original design, calculated by hand in the 1870s, is still functional. The engineers concluded that Roebling must have used a method of calculation that's been lost, a technique that worked, demonstrably worked, but isn't taught anymore. They combed through his notebooks, his letters, his published papers, but the method isn't documented. It was in his head, passed to him through apprenticeship under his father, John Roebling, who built suspension bridges in the 1840s and 1850s. That knowledge, how to calculate cable tension without computers, how to judge load by eye and experience, died with Washington Roebling in 1926. We have the bridge, we have the photographs, but we can't fully explain how it was built.
The Boston crane photograph wasn't an isolated case. As engineers began systematically reviewing old construction photos, they found dozens of similar anomalies. Photographs showing workers lifting stones that weigh several tons using wooden cranes, manual winches, no steam power, no hydraulics, just mechanical advantage. But the mechanical advantage, as calculated from the photographs, isn't sufficient. One photograph from 1887 showing construction of a courthouse in Philadelphia shows a crane lifting a granite block estimated at 8 tons. The crane is wooden. The boom extends 30 feet. The counterweight is visible, a pile of stones. Engineers at MIT analyzed the image. They calculated the forces, the torque, the stress on the wooden beam. According to their analysis, the wooden boom should have snapped. The weight of the stone at that extension would create a bending moment that exceeds the tensile strength of wood. But the photograph shows the crane functioning. The stone is suspended. The workers are calm. It's clearly a routine lift. The only explanation, the wood was stronger than modern wood, or the crane used a structural technique that distributed the load differently than modern engineering assumes, or both. Another photograph from 1902 shows the construction of a cathedral in France. Workers are lifting a carved stone archway weighing approximately 12 tons using a wooden frame and rope pulleys. The rope in the photograph is hemp, visible texture, clearly organic fiber. Modern hemp rope has a breaking strength of about 8,000 pounds per inch of diameter. The rope in the photograph is approximately 2 inches in diameter. That gives a maximum load capacity of about 16,000 pounds, 8 tons. The stone weighs 12 tons, 24,000 pounds. According to modern material science, the rope should have snapped, but it didn't. The photograph shows the stone suspended, the lift successful. Engineers who study the image concluded that 19th century rope-making techniques produced stronger rope than modern industrial methods. The fibers were processed differently, twisted differently, treated with compounds that increased tensile strength. But those techniques aren't documented. Rope making was a craft, passed down through apprenticeships. When industrial rope production replaced artisan rope makers in the early 1900s, the techniques were lost. We know it was stronger, the photographs prove it, but we can't make rope that strong today, not with hemp, not using traditional methods, because we don't know how they did it. One of the most disturbing discoveries involved scaffolding. In dozens of photographs from the late 1800s, construction sites show wooden scaffolding extending to extraordinary heights, 100 feet, 150 feet, sometimes more. The scaffolding is made of wood, lashed together with rope. No steel, no welded joints, just wood, rope, and joinery. Modern safety regulations would never allow this. Wooden scaffolding today is limited to 30 feet. Beyond that, steel is required. The reason, wood flexes. At height, wind load creates oscillation. The structure becomes unstable. Workers fall. scaffolding collapses. But 19th century scaffolding didn't collapse, or at least not often enough to stop the practice. Photographs from the construction of the Washington Monument, 1848 to 1884, show wooden scaffolding rising over 500 feet. That's a 50-story building equivalent, made of wood. Engineers at the University of Virginia analyzed these photographs in 2015. They tried to model the scaffolding using modern structural software. The models failed. The software predicted collapse at 200 feet, wind load, oscillation, buckling. But the scaffolding in the photographs stands. Workers are visible at the top, clearly functional. The researchers concluded that the joinery techniques used to connect the wooden beams must have been more rigid than modern joinery. The ropes must have had different elastic properties. The wood itself may have been denser or stronger. But none of those techniques are documented because scaffolding was built by carpenters, skilled tradesmen, and they didn't write engineering manuals. They learned by doing. Another photograph from 1910 shows the construction of a railway viaduct in Scotland. The scaffolding extends across a gorge, 200 feet deep. The wooden platform spans 300 feet horizontally. Modern structural engineers looked at this and said, impossible. The horizontal span would require steel cables, tension support. Wooden beams can't span 300 feet unsupported. But the photograph shows otherwise. The scaffolding exists. Workers are standing on it. The explanation, according to engineers who studied it, the beams must have been assembled in a specific geometric pattern that distributed load in ways modern engineering doesn't account for. Geometry-based structural support, not material strength, not brute force. Geometry. That's a lost technique. We know it worked, the photographs prove it, but modern engineering education doesn't teach it because it's not in the textbooks. Why? Because when steel became cheap in the early 1900s, engineers stopped using geometry to solve structural problems. They just used stronger materials. Geometry was forgotten, along with the techniques. The photographs also revealed tools, devices, machines, operating in ways that modern engineers can't replicate. One photograph from 1895 shows a pile driver at a construction site in Chicago. A pile driver is a machine that hammers wooden or steel piles into the ground to create foundations. The pile driver in the photograph is steam-powered, standard for the era, but the mechanism visible in the image doesn't match any documented pile driver design from that period. The hammer weight is too light. The drop height is too short, according to modern calculations. The energy delivered per strike would be insufficient to drive the pile into the soil type visible in the photograph. And yet, the photograph shows the pile partially driven, the machine functioning. Engineers concluded that the pile driver must have used resonance, a technique where repeated strikes at a specific frequency cause the soil to temporarily liquefy, allowing the pile to sink with less force. That technique exists in modern engineering. It's called vibratory pile driving, but it wasn't supposed to be invented until the 1930s. Yet the photograph from 1895 shows a machine that appears to use the same principle. Another photograph from 1888 shows a stone-cutting saw in a quarry in Vermont. The saw is water-powered. A mill wheel drives the blade. The blade is visible in the photograph. It's not toothed, it's smooth, a flat piece of metal. Modern stone cutting requires diamond-tipped blades or carbide teeth. A smooth metal blade shouldn't be able to cut granite. But the photograph shows a block of granite half cut with the smooth blade embedded in the stone. The technique? Abrasive slurry. Water mixed with sand is fed onto the blade as it moves. The sand acts as the cutting agent. The blade is just a carrier. That technique is documented, but what's not documented is how they kept the blade straight. Cutting stone creates enormous friction, heat. The blade should warp, bend, break. Modern blades are laser-cut, hardened steel, temperature-resistant alloys. The blade in the 1888 photograph is plain iron, visible oxidation, no special treatment. And yet, it's cutting granite, cleanly, without warping. Engineers who studied the image believe the blade was shaped using a technique called dressing, hammering the blade at specific intervals to pre-stress the metal, creating internal tension that resists warping under heat. But that technique isn't taught anymore. It's a blacksmithing skill. And blacksmithing as a profession largely disappeared in the early 1900s. The knowledge survived in isolated communities, rural blacksmiths, traditional tool makers. But it was never formalized, never written down in engineering textbooks. So it's lost, except for the evidence in old photographs. One of the most significant discoveries involved concrete. Photographs from the late 1800s show concrete structures, buildings, bridges, foundations, some of which are still standing today. But when modern engineers analyzed the concrete in those structures, they found something unexpected. The concrete is stronger than modern concrete. In 2011, a team of civil engineers at the University of California, Berkeley, studied samples taken from a bridge built in 1889 in San Francisco. The bridge was being demolished. The engineers were given permission to extract core samples from the concrete. The tests showed compressive strength of 8,500 psi. That's higher than most modern concrete, which averages 3,000 to 5,000 psi. The concrete was 122 years old. It should have weakened. Concrete degrades over time, exposure to water, freeze-thaw cycles, chemical reactions. But this concrete had gotten stronger. The researchers analyzed the composition, the mixture ratio, the aggregate used, and they found something unusual. The concrete contained volcanic ash, specifically a type called pozzolana, the same material used in Roman concrete. But the bridge was in San Francisco, not near any volcanoes. Where did the ash come from? Historical records showed that the ash was imported from Italy, shipped across the Atlantic, then by rail to California. Why would anyone ship volcanic ash from Italy to California in 1889? Because the engineers knew it made better concrete. The use of pozzolana in concrete was documented in Roman engineering texts. Vitruvius, a Roman architect, wrote about it in the 1st century BC. The knowledge survived through the Renaissance. Italian engineers in the 1800s still used it. But American and Northern European engineers didn't. They used Portland cement, cheaper, locally produced, easier to source. And Portland cement concrete is weaker. The engineers in San Francisco who specified Italian volcanic ash knew something that modern engineers forgot. Concrete isn't just about strength, it's about durability, longevity. Roman concrete structures are still standing 2,000 years later. Modern concrete cracks after 50 years. The difference is the ash. But that knowledge disappeared in the early 1900s. Why? Because Portland cement companies monopolized the market. They funded engineering schools, published textbooks, trained engineers to use their product. The use of pozzolana wasn't taught, wasn't promoted, wasn't economically viable. So it disappeared. Except in old photographs, which show structures built with it, still standing, still strong. One of the most fascinating discoveries involved ironwork. Photographs from the 1800s show ornamental iron, gates, railings, structural beams, often with intricate decorative elements. Modern metalworkers look at these photographs and say, we can't do that anymore. Not because we lack the tools, but because we lack the technique. 19th century ironwork was forge welded, 2 pieces of iron heated until nearly molten, hammered together. The bond is molecular, stronger than the surrounding metal. Modern welding uses electric arc or gas flame. The weld is strong, but it's a different structure. The heat-affected zone around the weld is weaker than the base metal. Forge welding doesn't have that problem. When done correctly, the joint is seamless, indistinguishable from a single piece of metal. But doing it correctly requires skill, experience, the ability to judge temperature by color, the rhythm of hammer strikes, the exact moment when the metal is ready. That knowledge was passed from master to apprentice in blacksmith shops over decades. Photographs from the 1890s show blacksmiths working, forges, hammers, anvils. You can see the process, but you can't learn it from a photograph because the critical information, the feel of the metal, the sound of the hammer, the color of the heat, isn't visual. It's sensory, embodied, tacit knowledge. When factories replaced blacksmith shops in the early 1900s, that knowledge was lost. Factory workers operated machines, pushed buttons, followed instructions. They didn't develop the intuitive sense that master blacksmiths had. In 2003, a restoration project for a 19th century building in Philadelphia required replacing some ornamental ironwork. The original was damaged, needed replication. The metalworkers tried. They used modern welding. The result looked similar, but it wasn't the same. The modern welds were visible. The joints were weaker. The decorative elements didn't have the same fluidity. So they hired a traditional blacksmith, one of the few remaining craftsmen trained in forge welding. He replicated the ironwork using 19th century techniques: forge, hammer, hand tools. The result was indistinguishable from the original. But here's the problem. That blacksmith is 76 years old. He learned the techniques from his father, who learned from his grandfather. The lineage goes back to the 1800s. When he retires, the knowledge goes with him, because there are no apprentices, no one willing to spend 20 years learning a skill that's economically obsolete. The photographs preserve the evidence, but not the knowledge. So what do these old photographs actually reveal? They reveal a pattern, a systematic loss of knowledge, techniques that worked, materials that were superior, methods that produced better results. All lost, replaced by industrial processes, standardized, cheaper, faster, but not better. The engineers who discovered these anomalies weren't conspiracy theorists. They weren't trying to prove ancient aliens or lost civilizations. They were doing routine work, digitizing archives, studying historical structures, trying to understand how old buildings were made. And they stumbled onto evidence of something uncomfortable. We're not as advanced as we think. In some ways, we've regressed. We can build taller, faster, cheaper, but can we build better? Can we build things that last 200 years? Most modern buildings are designed for a 50-year lifespan. Then they're torn down and replaced. But 19th century buildings are still standing, still functional, still structurally sound. The difference isn't materials. Steel is stronger than iron. Concrete is more versatile than stone. The difference is knowledge. The 19th century builders knew things we don't, techniques we've forgotten, principles we stopped teaching. Why? Because industrial capitalism prioritized speed over quality, profit over durability, standardization over craftsmanship. It's not a moral judgment, it's an economic reality. A building designed to last 200 years is expensive. It requires skilled labor, quality materials, time. A building designed to last 50 years is cheaper, faster, more profitable. So the market selected for the cheaper option, and the knowledge required for the expensive option became economically obsolete. The master craftsmen retired. The apprentices became factory workers. The techniques were forgotten. And now, when we look at old photographs and see things we can't explain, we realize the knowledge is gone.